To the Teruko Yata lecture, memorial lecture. Today we have a very special guest, a true pioneer in the field of robotics, Professor Ruzena Bajcsy. She received a PhD in electrical engineering from the University of Bratislava in what is now the Slovak Republic, was Czechoslovakia then. She then received a second PhD in computer science from Stanford University. She then moved to UPenn and created as a professor there, and created the GRASP lab, which all of us know, of course. She also served at the National Science Foundation, where she oversaw all of the funding basically for robotics, AI, and related topics. She's now a professor at Berkeley. She was the director of the CITRIS, the Center for Information Technology Research. Professor Bajcsy is a true pioneer both of the field of robotics, but also as a person. So let me give you a couple of statistics here. She was the first female PhD in electrical engineering in Czechoslovakia. She was the second female CS PhD when she was at Stanford. And she was the first female faculty in engineering at UPenn. So that's an interesting trajectory that is worth noting. Let's welcome Professor Bajcsy today.
Thank you. Do you hear me well enough? It's really my pleasure, and thank you very much to inviting me to this special occasion. And it's always wonderful to come back to Carnegie Mellon, which of course we all admire, and happy to return. So what I am going to talk about today is really when I came to Berkeley. Before that, I spent almost 30 happy years at University of Pennsylvania in Philadelphia, and I worked on standard robotics, computer vision and touch and manipulation and all kinds of, typical things. I did work, I guess, a little bit on the mobile robotics, but much more on manipulation. So when I came to Berkeley, I came as a founding director of this CITRIS, which is a center in information technology in service to society. And it's fascinating because, when I took this idea of service to society very seriously, and I started to go around the university as such and try to explore how to deal with humanities, social sciences, and arts, and we developed, several pioneering demonstrations that I couldn't raise money eventually, so I had to give up, but now they are in vogue. So the first thing we did was we built a lab, a teleimmersive lab with 42 cameras where we captured in real time a dancer. And I collaborated actually with my daughter, who is in Urbana-Champaign, and she developed a similar lab. And so we demonstrated that you can bring two dancers who are physically remote, but together in the same environment, and in fact do the touching. We called it virtual touch. But as I said, this was in 2004-05, and we couldn't raise money for that. Later on, I tried to impress the humanities that this is a time to really take computer science seriously. And now, luckily, to my great pleasure, there is a program in digital humanities, and also the architecture school, who kind of said, oh, well, Ruzena, just give us the money and leave us alone, did now are teaching and pursuing. So I think the moral of this whole story is that, and this is, I talked to Herbert a little bit about that, and I promised I mentioned this, that academia should be at the frontiers of the technological development. So yes, it's difficult to sell it when you are ahead of the time, but this is our job. And my concern right now is that what people talk about artificial intelligence, and I can tell you, Raj Reddy and I were there in the very beginning of what artificial intelligence started. What today artificial intelligence is standing for is for this machine learning, and in particular, actually, much more restricted idea of machine learning, which is this convolutional network machine learning. The industry, and as you know, I live in Berkeley, the industry is going gaga about this. I mean, they are all putting money into it, investing, grabbing our best faculty to work in the companies. And I am really concerned, and I plead with you guys, the students in particular, that you need to think about things that are not 2 to 3 years, but 5 to 10 years problems, so that the industry can flourish. Because right now, what the industry is benefiting from is what we did collectively in the last 10 years or so. I mean, this whole convolutional network is not such a new idea, but because you have all this compute power and memory power, you can really implement it, and that's why so my plea to you is universities must take care of the future ideas so that industry and we collectively as citizens benefit from the technological advancement. So when I stepped down as a director, I, being an older person, as you see, I started to think about how technology can help aging population. And that, being a person who teaches robotics, brought me to the problems of what I am trying to model. This is not machine learning. I am doing strictly systems identification model, what the kinematics of individual is, setting up and asking what kind of observational mechanisms I have to develop in order to be able to get this individualized model. And the reason for that is that as you get older, your muscle capabilities weaken, your reaction time slower. I mean, everything kind of slows down, okay? And my hypothesis about the technology is, but it never goes down to zero. Even if you have a stroke, you cannot move, but you can a little bit move. So our technology should be able to assess, measure how far can you go, and only remedy, give you help as much as you need it. And the reason for that is that if you don't do that, then atrophy sets in. You know, don't use it, you lose it. So this technology that I am trying to develop is helping you to exercise as much as you can so that you don't lose your own capabilities, but help you so that you can live independently. That's the overall goal. So let me just show you. So what we do so we are trying to develop these measurements. And I will talk greatly about the measurements of dynamics and kinematics in a non-invasive fashion. That's the key, okay? And that what can technology help you? And so then we identify, so you have here in the middle, you have this blue or the green, the capabilities, what you can do, how far can you reach, you know, how fast can you walk, and so forth and so on. And then whatever we find in that red is sort of your disability, then we complement your abilities with what's desired in order to be able for you to pick up a glass of water, reach your head, your mouth. I mean, you know, just have the basic capabilities. And so then we build, I work with some mechanical engineers who build these, what they call the assistive devices. So you can build a sleeve, or you can build a wrist, or you can build some braces to help you to walk. But the key difference from what we do from the typical mechanical engineers is that we equip it with also sensing. So think about it. I had a problem of opening a jar, and so you need an extra torque. So you really want to measure how much your own wrist can move, to rotate, and then just supplement as much. And that's a very nice control problem. It's not just mechanical engineering. Now, there is another problem there, which I throw it out to you folks, and that is how to energize these assistive devices. So the standard thing is you use motors, okay? But they need batteries, and batteries are heavy. So you really need to think about what energy source you want to use which converts easily and efficiently into a mechanical energy, because that's what you really are after. And so what we have been playing with is a compressed air. But I am challenging you that you should think about also some other, like hydraulic or maybe even chemical energy, because the compressed air, the nice thing is that you can energize the whole thing for lifting a cup of coffee or whatever else you need to lift with a little bomb that you use for siphon, you know, the old days that's what we did for your sparkling water. But anyway, and you can recharge it every night, just like you are recharging your cell phone. So and you don't have to carry things that are heavy. But obviously it's not the last word. So, all right, so what we are after, this is sort of and we are collaborating with University of California, San Francisco, the medical school, and for physiotherapy, neurology, and orthopedics. And we are trying to, as I said to some of my friends, that I moved from electrical engineering through computer science, and now I am really more as a mechanical or biomechanical engineer. So I'm trying to do this Kinect-driven goniometry for muscle force and spinal load estimation, affordable methods for assistance and augmentation. And we are also measuring fatigue. And I will explain that later, yes. So this is our body on those, where you see those points we can measure. And you have to have a experimental design, right? So our methodology is that you stand on one leg, okay, and you do squat, and that's how we measure the data that I will show you. So the rigid body model, pin joint, fixed limb legs, right. Nevertheless, the beauty of this observational technology is that it's very individualized, and you are all very different. And I have a last slide to show you that even your skeleton is different from person to person. So here it is. We have 7 spherical joints, right? And then we have cylindrical joints, and those of you who don't speak this language, spherical is that you can rotate in 3 planes, okay? And the cylindrical is that you can translate, but then also rotate in two different planes. So that's what we have, and we measure on those points with the motion capture, which I hope you have seen or you could see. I'm sure that CMU has a lab like this, so it's not. And then you can display what you really see in terms of just kinetic assessment. Now, when you collaborate with doctors, one thing that I learned the hard way, they are very concerned about 2 things. One is simplicity, how to use things. They don't want to be bothered by long explanations. I joke, they like 3 buttons, red, blue, green, you know. And the other one is cost. You know, if you really want this technology to get to their hospitals, it has to be cheap. So while the motion capture that I have in the laboratory is quite accurate in terms of measuring the X, Y, Z, and also the angles. What the doctors really like is the Kinect camera, because it's $150. And it gives you, so we had to do calibration. And people don't like to bother with calibration, but for example, here I'm showing here, if you see that little X, the difference between the Kinect estimate of the position and the phase space estimate of the position. So one thing you have to show the doctors that yes, it's $150, but you, on the knees, for example, you will have a difference of 3 centimeters of the position estimation. So it's that's what you get from having a cheaper system. And so here is the angle recovery. You can see, because you do this, so you can measure the nice periodic change, but then in the center, and I believe this is data from me, you are not as stable, so your center of gravity is not as nice periodic, and as you can see, the blue is showing the vibration of your center of gravity. So just to show that what we measure really corresponds to reality. And then we also, in our laboratory, we have a force plate, which can measure the forces, but only the gravity, the gravity force. So the force plate is like a more accurate bathroom scale, but that's all what but it tells you the vector in 3 different directions of the forces. So we have here the forces, so you can see again you have this forces in the center of gravity. As you do this periodic movement, but then on the other side of the legs, as you can see, there is no real change. There is some noise, but obviously, but not real change. And then the estimate of joint load, because you are doing this, and this is, I think, data from me, as you can see, is very uneven. I mean, if it would be with some younger person, it would be nice periodic load, but you know, Grandma Bajcsy doesn't have that. So then we can also do the estimation of spinal load, and this is just a demonstration that we can get that from just to argue with the doctors that what the Kinect is giving with some more accurate vision system, that we can get some reasonable agreement of this measurement. I will show you now. Okay, so as I said, we are collaborating with some people. I think this is orthopedics. Anyway, your spinal problems can get very serious. If you didn't have a slip disc, you probably don't know what I'm talking about, but it could be extremely painful. And regrettably, if it persists, and this unfortunately is not just a problem of older people, but it can hit anybody. It's a younger problem that you can get a slip disc. Now, unfortunately, the remedy for that is that the doctors, unfortunately, are butchers, in my opinion. They will drill 2 holes into your vertebrae and put a steel plate to keep the disc not slipping and just keep you kind of straight. Now, regrettably, it works sometimes, but not always. And so one of the problems that we would like to understand is under what circumstances it doesn't work, and have some prediction so that these poor patients who go through all this pain with the drilling holes and so forth in their vertebrae can avoid that. So here is a modeling of the spine joint centers, and it's fascinating because it's really a kinematic model, and it's a model of, you can model it. In fact, I really would like to model it on using measurements on each vertebrae. But that, unfortunately, is not simple. So right now we have a 1-degree model, or 1-joint model and 2-joint model. The reason for that is, ladies and gentlemen, is that your skin is moving. And so it's extremely difficult to fasten sort of the markers on your vertebrae. The only possibility is to have an X-ray. But unfortunately, the X-rays are not admissible because of radiation. So we have done this estimation, and it's a very simple 1-joint model and 2-joint model, and then we just take several measurements and do optimization-based method for estimating spinal joint center. It's optimization in a sense that you take several measurements and you look for the center of those measurements. And then motion of torso and pelvic frame during flexion and extension. The experiment is like this. Yeah, kind of moving back and forth, and that's how you test your points of flexion and deflection. So here it is. So here is, you can see how it can visualize. And as I said, I would like to know a little bit more the details, but with these non-invasive technologies is not so simple. Actually, this problem of skin and fastening is a more generic problem. Recently, I have been exposed to the problem of prosthesis. So think about it, that we have a patient right now who lost his arm from here down, all right? So you can, and in these days with 3D printing, you can design, prosthetic arms and hands with 5 fingers and so forth and so on. But what you really want is to connect this prosthetic controller with the cables with the remaining muscles that you have here, okay? And you can do that because you can measure the MEG, the EMG, the electrical myography, which really signals from your brain to the muscle go, okay? And that's what you really want. And you can measure that. All right, but the problem is that with this prosthesis, how you fasten them to this part of your arm that has still alive muscles is really a challenge, because your skin, and as you get older it gets worse, your skin is moving. So if you fasten it very hard, then it hurts. If you keep it comfortable, your localization is not very good. So it's really, this is really the interface we talked about with somebody, I think, the human interface of these machines is non-trivial. Okay, so here is our gadget for your lifting. Okay, total mass and mass on arm, that's a problem, how to make it light, and 9-volt battery, and cost less than $500, okay? So that's what's happening here. So then we had this very interesting problem from our neurologist who has stroke patients. And the stroke patients lose their capabilities of moving their arm, okay? But they keep their capabilities of the tactile perception. So here is the design of a very simple gizmo, and which is a table which has a 2-dimensional moving device, so that we can control the arm moving in XY table. But then we had to design a little tactile sensor, the force sensor that holds and gives you the positioning, so that we can control based on this position which way the arm should move. But then the subject has also a glove which has holes to protect the tactile sensation, because the tactile sensation through EEG cap tells the brain that I have touched, and that signal then gets detected through EEG and goes to the arm controller. So I will show you the video now, how it works. So you see below there is the positioning device, and here is the tactile sensation is preserved, and it's signaled to EEG. I will show it to you again. And so the computer tells move, all right, then the human touches, knows the tactile, and then can tell back to the computer driver of this position. The idea here is we have just tested, this is just very recent, we just tested it in our lab last week, and I believe this week or next week we are transporting this to the hospital so that people can. Now the hope is through the neurologists that the subjects are going to use it as an also exercise machine so that they can possibly recover some of their lost capabilities, and that of course needs to be tested and seen whether that will work. All right, so okay, so now, so this is all kinematics, folks, and some position force impedance control, okay? Now, what I'm really focused on as a scientific endeavor is to understand the muscle, because the muscle is your motor, and you have muscles all over your body. And so to me, it's foundational. What can we learn about the muscle, how the muscle contracts, which will give you how strong your motoric capabilities are. And as you know, as you get older, this is of course decaying. Now, muscle is an interesting device. It's only a translational device. It just changes the length. So then you can ask, how do we do the rotation? And this picture should show you the reason we do this, because we have several bundles and they are oriented differently, and so the rotation is a composition, what the medical people call as a synergy of different muscles with different orientation. They then provide the rotation. So it's quite complicated. Furthermore, I want you to notice that each muscle bundle has muscle fibers. And regrettably, I don't have very good way of resolution to measure the muscle fibers. So that's one of my handicaps. So human dynamics model is essential for many applications. Understanding forces imperative in physical HRI. So I really believe that in order, first of all, to understand the muscle is really foundational problem, especially the non-invasive way, and the medical applications are tremendous. But I also believe that as we are proceeding with this human-robot interaction, in order to have predictive way of behaving the system as such, you can really model very nicely the robot, but we really need to understand what the human can do. And I met this morning with a cognitive scientist, Professor Klatsky, and she really convinced me that the cognitive aspect really interferes actually with your motion, your motion. And so the intentionality of the human as it expresses through its motion is very important to understand. Anyway, it's difficult, complex dynamical system, morphological variation, everybody is different, of course, and limited sensing. So let me show you what we do at this point. So there are other approaches than what I am trying to do, which are based on cadaver measurements and assumptions and literature. But what we really are trying to do is morphological data, MRI, ultrasound, and then real time, because you really, in order to really measure how how hard your muscles can move, you really have to measure the dynamics, and there is no other way to do that. So here is a model that we have worked, very simplified, very trivial. It's kind of, the model, as you know, is in between two joints, okay? So the model, the muscle is between two joints. The fact that you can move this is because of your muscles. You have hinges, but the force, the energy that you can do this comes from your muscle, okay? So remember that. And so we have set it up, I don't know how much I want to go into. I mean, we measure these. What we really are after is a muscle activation. We measure the length, we measure the force, because we can push a robot. That robot will tell us what is the reactive force, that's your FM there. We can measure the torque, the TIN, and we can measure these RL and R and theta, all these kinematic. So here is your some setup, and via single channel. So we have the EMG. The EMG, folks, is the electrical myography. Myography stands for the muscle, and electrical, it's electrical potential is generated as from the signal from your brain. And AMG, I will explain a little more, that's an acoustic myography. And the acoustic myography, there are several theories, and we are still sorting out which one we believe. But basically, the acoustic myography is based on the fact that your muscle fibers resonate. And the way how you can, this has been known since the 1920s, that the muscles resonate, especially when you are in very cold, you shiver. And that's the effect of the muscle vibration, okay? And so what this AMG does is basically a glorified microphone that measures the frequency of this vibration, okay? But how to interpret it, whether you take the string acoustic theory that you apply to it, or there is another theory on the more molecular level, it's not obvious at this point. So we are trying to sort this out. Anyway, so here is the EMG, surface electromyography, sensitive noise and based on neurological signal. And here is the acoustic myography, improved signal to noise ratio based on physiological signal, and is new. All right, so here is an example of EMG, what it can. So as you can see how much noise there is, that whole yellow is noise. The AMG is much better in this regard. In forearm, the biceps, you measure that. So I have been struggling with how to interpret this. And this is from the inventor of the, well, the inventor of not the principle, but of the microphone, Mr. Harrison. And here you have this AMG, which is showing you that you have a big spike, you have an amplitude above a certain threshold, and you could measure that. But this is the interesting thing that I wanted to share with you, which I really didn't know. Notice, if you exercise your muscle and you measure EMG, the signal is not everywhere the same, all right? The EMG, as you see here, is in the upper side, you get this signal, then in the middle, you get nothing, all right? And then again, lower you get a signal, and then less of a signal. So what it says, and this is the fascinating stuff to me, is that the motor units are not assessing every fiber in the muscle in a consistent fashion, that they are selective. And I think my explanation of that is that the reason for that is reliability. The Mother Nature doesn't want to put all the chips into one basket. So it kind of distributed, you see? And that, I find it fascinating, but at the same time challenging, because then I have to figure out which one I need to measure when I measure with the acoustic. So look what the acoustic is doing. So wherever I have EMG, okay, then below I have the acoustic, okay, and I have to somehow synchronize, you know, when the motor unit is saying to the muscle, small bundles, go, you know, then as you see with some delay, I can measure the acoustic, the vibration. And so that's what's happening, and that is quite exciting. So here is, we did some subject AMG examples, and in various different biceps, but I think I will not go into any great details. More, I will try to tell you that what we really think that the way how we need to process this data, AMG, and we are just starting to set up the more subject experiments, is that the amplitude tell us how many of the fibers the motor unit has attacked, okay, the amplitude. In other words, how many fibers are being resonated, that shows in the amplitude. And the strength, how much it stretched or shrunk, is measured by the frequency. That's what our current hypothesis is. And if you allow me, maybe in 6 months, come back and I will tell you whether it's true. But in addition, you know, nobody who is in the measurement business will trust just one type of measurement. So we are also looking at with the ultrasound. And the ultrasound, we have a way of, it's like, you know, it's like this. It's a handheld ultrasound, and you are kind of going like this and looking at the time space over cross sections, how the cross section of the bicep changes, and from that you are hoping to extract the length change, okay? So, but here is an example to show you how difficult these ultrasound images are, and this is inactive, and how do you measure it? It's still a matter of our research. So, so I will show you and I will get back then to maybe show you more.
In this work, we propose 2D ultrasound as a means of extracting muscle deformation and explore the feasibility of applying this signal to exoskeleton and prosthesis control as a measure of muscle activation that is more robust and localized than that provided by surface EMG. To understand and quantify both load-related muscle deformation caused by muscle activation and configuration-related deformation caused by muscles passively stretching and colliding, we collected 9 volumetric scans of a single subject's biceps brachii under varying loads and elbow flexion angles. Raw ultrasound data were collected from the anterior surface of the arm and localized using motion capture to build a 3D intensity map that clearly shows the fascia between muscles and the surfaces of bones. Volumetric data of the biceps brachii and surrounding structures were then manually extracted. These extracted volumes show substantial deformation under both changes in elbow angle and changes in muscle load, confirming the importance of modeling both signal sources. Despite these variations, the spatial location of maximum deformation under loading, as measured by the maximum change in cross-sectional area, remains approximately consistent across elbow angles, suggesting an optimal location from which to extract a control signal. In future studies, these data will allow us to build a more nuanced understanding of the way force and configuration-associated deformation signals interact, enabling both the validation of existing muscle deformation models and the extraction of robust signals for assistive device control.
Okay, so what I wanted to tell... No, I don't want this again. Sorry. Okay. One interesting insight I got, and maybe some of you think this is trivial, but even with the passive, just different kinematic configuration, the muscles are extending or shrinking. And the reason for that is that, think about it, as you have these two skeletons, and you have, think about like a string of a rubber, all right? Depending on how you are moving your hinge, the rubber has to stretch or shrink. And that's exactly what we have measured here, okay? So now, this works even if you don't hold anything, which is not dynamics, just from the kinematic static configuration, the muscle strength has to change, okay? Now that gets compounded with when you add some, real dynamics strengths to move around, to deal with the real. So I came to conclusion that actually this muscle activation is at least composition of two things. One is the kinematic position, and the other one is the task or the force that it has to carry out. All right, I checked my clock, so I think I better start to conclude. So there exist frameworks for human modeling. There is OpenSyn. This is Professor Delp from Stanford, who has been very famous and did all of this from cadavers. Task-specific models, our own models, but do not exist frameworks that tell us how good these models are. And this is really a question that is begging some research, how good these models are. And of course, the difficulty is because of the variation of different people. So think about it. We have done some 10 subjects, full arm MRI scan, hands through torso, vary in age, health, height, weight, gender, and 4 separate scans taken to improve contracts where possible. Then, in order to get the proper resolution, we had to take MRI, piecewise and then stitch them together. So it was a classical image processing problem, but anyway, they did it, Laura, and so hand, forearm, elbow, and so. So look at the quantitative model, segmental muscle. This data came from Stanford, and notice how complex it is. So that is what we are dealing with when you are dealing with human. So you need the extract parameters of interest, bone muscle volumes, bone muscle lengths, muscle bone attachment points, and then compare parameters across subjects, across per troop subjects. And this is all our future work. We are just inch by inch getting there. So here is a transformation. You can see how detailed it is. You see the shoulder is a very complicated system, as you can see. And this is atlas, and then the subject, target, and how you get there. And here comes your typical registration. I'm sure Herbert would relate to this. You know, how to automate this whole process is a challenge for us. Okay, so here is some quantifying model accuracy. So you want to really look at it. You have a volumetric reconstruction, and then you want to look at the different cross sections. And so this is really the punchline, that even the skeleton, you think that we all have the same skeleton. Well, we don't. Okay, look at these differences. Bone segmentation results show significant morphological variation across subjects that cannot be modeled in existing frameworks. So, all right, so I am concluding. Robotics as a field has great need for modeling and predicting human capabilities limitations. Remember, all the people who are working in these human-robot interactions have this need. Robotics is a great tool for modeling human systems. The outstanding question is to connect the biochemistry with biomechanics. And the reason for that, ladies and gentlemen, is that, and I started to mention this to you, we are able to measure, for example, fatigue, which is related to your strength of your muscle. But the way how we do the fatigue is we measure sweat, and I collaborate with a colleague who is basically a chemist, who can take your sweat if you work hard, you know, exercise or so, and take your sweat, and he can analyze how much sodium, potassium, calcium, and so forth you have. But it's global, okay? It's global, it's not localized. So it's global, but it can tell you, and that's where the biochemistry comes in, that if we can identify what your mechanical problems are, and then relate that to your biochemical, then we are crossing the different scales, because then the remedy would be very different. If you have a biochemical problem, then you need more vitamins or something, some chemicals. If you have biomechanical problem, then we can create these assistive devices. So that is, but regrettably, to my great astonishment, these two communities don't talk to each other. The biochemists, they work on the molecular level, and they take tissues and they use it through the microscope, electron or other microscopes, so they work on very isolated tissues. I am interested in the living objects, so how you cross these scales is really a challenge. This is a basic scientific question, how to elevate measurement signals between different scales of observables. Yeah, in our works, we work on this. So, thank you very much.
These questions, of course.
Of course, Chris, yes.
So the great ideological debate we're having now is between careful modeling, descended from system identification,
Right,
and what are politely called data-driven models.
yes. The whole morning I spent on this question
You
with...
don't even have to be polite.
Yeah, no, with Raj Reddy and Roberta Klatsky and so. Look, being an old, I have been in this business 50 years, so I remember and I can recite the history. To me, the truth is never one or the other, you know. We are engineers. We test, we measure, we design, and then we go on, right? So, you know, to me, data is important, but I will say that you have to be careful how you collect the data. Garbage in, garbage out. As you know, my colleagues in computer vision, for example, they spend, I don't know how many hours to find pictures of dogs or pictures of elephants or whatever, you know. So they use the human eye to do some pre-classification, and then they deploy their data-driven stuff, all right? To me, it's crazy to ignore structure. And physicists who introduced this reductionism into, you know, came because they felt that it was useful, the reductionism. Now, everybody understand, or I shouldn't say everybody, most of us understand that reductionism is not the full story because you have distributions, right? And Raj was telling me how proud he was that actually in speech, it was Carnegie Mellon that recognized that, you know, the speech is not just strict phonemes, but there is the Markov process of probabilities and all that. So look, Mother Nature knows that, you know, Mother Nature doesn't know step functions or Dirac functions. Those are inventions of our brains for making simplified models. But it gives us gives you a microscope, no, gives you a telescope to see through the complexity. That's really the advantage, in my opinion, of the reductionism.
Speaking of data, and the slide that you showed on quantifying
Yes.
accuracy, it seems like you were still using a small number of subjects because of the complexity of the
That's right.
data. What are the prospects of scaling that up, basically?
Well, so I have some other slides, of course, and I'm happy to share with you. We have tried this. You have to get this out of your lab to the real world in order to test it in the real world. And so we collaborated with a doctor who had a muscular dystrophy patients. And there, the muscular dystrophy is a disease that is a genetic disease. You are born with it. At age 5, children start to fall. And at around age 15, they die because the muscle crushes your skeleton. That's the disease. And currently, they don't have a cure. But they like to monitor it and experiment and all that. So we have designed for them a very simple system which can just do this, this, and this. So it gives you a workspace, basically, volumetric. And you can see that these Duchenne people, the volume shrinks as you go on. You know, you can go this, you can only do this, and so forth and so on. So there we have looked at the accuracy problem with respect to Kinect, because the hospital doesn't want our face space. They just want the Kinect. And for them, it's better than what they do, which is right now they are eyeballing. That's the state of the art. So we have some results on, you know, the accuracy. For example, the knees, you know. So if you really want to focus on knee replacement or so, then you need more accuracy, and then they are focusing on that. and they are willing to do that. Yes, please. Yeah.
Hi, yeah, I thought it was an unbelievable body of work that you presented. I was very interested in the spine kinematics that you
Yes.
discussed in the beginning. And you were saying that you used two markers as opposed to
Right.
You said that's a very hard problem. So I'm wondering if you could discuss a little bit what the challenges are with that.
The challenge is your skin. Your skin is moving, and because of that, but that challenge is not only on the spine, but in the spine we see that much more evidently, but it's also in any amputee kind of devices that you want to fasten on the partially working human limb. How to do that, it's not trivial. Yeah. Now, I will tell you, my colleague, and you probably know Jan Rabai, who is a sensor, micro sensor kind of person. So he developed these EMG, this electromyography, at the nano level. And so his approach is implant. But I'm not sure that, first of all, we really don't know how the body is going to react to these metals, It's still a matter of research. So I'm still hoping to do things non-invasively. But maybe I have to give up. Yeah.
Other questions? Thank Professor Bajcsy again.
Thank you.